So in this video, we're going to talk about different techniques for describing vectors mathematically in three-dimensional space. So you may recall that in the prior set of videos from Tuesday's lecture, we talked about doing this same process in 2 dimensions. This content is covered in section 2.5 of the text, but unfortunately that is meaningless to you because the publisher and the bookstore still can't seem to figure out how to get your textbook right within Canvas, in spite of emails twice a day from me now. Hopefully they'll get motivated and actually get that up next week. But in the near term, I am just going to copy pages from an older version of the textbook physically that I have and get those posted whenever I get to work today. You can probably look at the timestamp on my computer and see it's like 5:30 a.m. in the morning. So before we talk about describing vectors mathematically in 3 dimensions, let's just step back and think about how you describe them in 2 dimensions. So you are looking at a 2-dimensional plane when you look on the screen of your computer or phone or tablet. So if I have a vector like this, we talked about 2 different ways that we can actually put numbers that describe it fully. The first way was kind of the natural way that was based upon geometrical techniques. I could just tell you how long the vector is, and I can tell you its direction, described as an angle, measured from some reference axis. So traditionally, we use the horizontal axis in order to kind of serve as a reference for our angular displacement. And we measure that angle in between the vector and that reference axis, and that was called a polar form description. We talked about the magnitude and we talked about the angle. However, even for any reference axis, there are always 2 different ways in 2 different angles that you can specify in order to describe that direction. So you have to have a convention. For example, if this is my vector and this is my axis, I could talk about the smaller angle here, or I could go all the way around and talk around the larger angle. So we did give a convention. We said it's usually measured from the positive x-axis in the counterclockwise direction. We call that a positive angle. If the angle is reported as negative, that means that it's a clockwise rotation from that axis. However, one of the things about this text, when you use it in statics and dynamics, is they rarely hold you to reporting in that convention. It's also okay always to either draw a particular, when you have your vector drawn, I should say, to actually mark up which angle you're talking about on your drawing, or oftentimes they will even ask you for a different, for an angle measured from a different reference axis. So that's the geometrical approach, where you talk about the magnitude and direction. In addition, we kind of talked about more of a linear algebra approach, where you just described it by a set of 2 numbers. And those 2 numbers were known as the components of that vector. And the way that we did that is by taking the vector in 2-dimensional space. Remember that a vector is represented by an arrow. An arrow has a tip and it has a tail. And if you drop a perpendicular, ideally to the horizontal axis, even though you could do the same thing to the vertical axis, as long as you keep your trigonometry straight, you use your right triangle trigonometry and you break that vector down into a component in the horizontal and vertical direction. You could just take the weights of those 2 components and just report those as a weighted linear combination of I hat and j hat. We also talked about the angled bracket approach for describing. So in 3 dimensions, it's going to be the exact same. We're going to talk about 2 general classes of approaches. The first that we'll talk about is an analogy of vector form. So it's probably not surprising to you that since 3 dimensions is just adding another dimension to your 2-dimensional space, that really all we need, we can use the 2 basis vectors that you may recall we talked about, I hat and j hat. However, when we have that additional dimension of space, which here, your book will kind of always draw that additional dimension as coming out of the ground, for lack of a better term. If you view a plane and on the bottom, on the table in front of you as sitting down on that or on the floor or something of that nature, the z-axis, they will actually define as coming out of that vertically with the positive axis going up. Typically, we'll talk about when we get to the concept of curl, that the convention of z, the sign convention of positive z, follows a right-hand rule. If you curl x into y, your thumb points in positive z. So naturally, if you're going to describe a vector in 3 dimensions using this rectangular form or linear combination of basis vectors approach, we just need a new basis vector, and we're just going to call that k hat. So notice that positive k hat is 1 unit long and goes up along the positive z-axis. In addition, we're going to talk about some polar-like approaches, but it's not going to be as easy here because if you think about, go back to what I was describing earlier, and put this vector anywhere in 2-dimensional space, what you actually notice is when it's in 3-dimensional space, you're actually going to need more than just 1 reference axis. So there's 2 different ways to talk about this. The first is magnitude and coordinate direction angles. And coordinate direction angles, the way that your book does that, is they take the vector anywhere in 3-dimensional space. So now it's coming at you a little bit. And if you have some coordinate axis, say the purely horizontal direction, naturally I can take the vector and the axis and I can form a plane, and I can measure the angle in between them. And that's called the coordinate direction angles. Another thing is I can use what are known as spherical angle descriptions. And this is probably more what you're familiar with from your math class. The way you traditionally do it is you take the vector and you lay it along the x-axis and you rotate it in the xy plane some certain amount. And you call that the azimuth angle, how much rotation is in that xy plane. And then once you get it to the ideal point in the xy plane, you elevate it. So if you notice there, I'm also describing the vector by two angles, an azimuth and elevation angle. However, in both of those cases, right, when I do azimuth and elevation, that just tells me the line of action of the vector. In order to describe it fully, I also need the magnitude. So each of these descriptions, you're going to need defining coordinate axis, you're going to need unit vectors, and you're going to need angle measures. And we kind of alluded to some of those already, but we'll look at them in more detail in the coming slides. So there is the way that the book will generally do a three-dimensional axis system. Again, they're going to use the floor as the xy plane, and they're going to have positive z coming out of that in the upward direction. However, you can, whatever you pick for x, y, z, let me rephrase that. Whatever you pick for X and Y, as long as you take and we'll talk about the curl later, but just to foreshadow it, if you take the base of your right hand, align it on the X-axis, curl it towards the Y-axis, your thumb will point in positive Z. So in that case, you're kind of got it like this. You got X coming out, curl towards Y. Notice that Z is pointing up. So in terms of rectangular components of vectors, as I mentioned, we're going to add this additional basis vector along the z-axis, just following in the convention. If I and j are along the x and y axis, then z will be along the k-axis. And the book is going to show you, again, I think it's a little bit confusing because they talk about components as actually being vectors. When I think about the components of a vector, I think about the weights that are scaling the basis vector. However, do note that it's just a matter of convention, and eventually you won't be confused at all. You can take any vector and you can write it as a sum of vectors along each of the three axes. And since you have a unit vector along each of those three axes, I hat and j hat and k hat, you can take each of those vectors and decompose them into a pure magnitude times a basis vector. And the reason that you can do this, the reason that you can go from this, if you think about it, ax is the entire vector along the x-axis. And the reason that you can write that in terms of its magnitude times I hat is because of that scaling property that we talked about previously. Magnitude of I hat is just 1. So when you multiply by the resulting term that is left has to be the magnitude of that vector along the x-axis. So now let's actually look at some angular-based descriptions. First and foremost, before we do that, the question is, how do we describe actual magnitude in 3 dimensions? Well, it's going to be very similar to the formula in 2 dimensions if you're just a formula memorizing person, and that's okay as you're getting started. It's just going to be the square root of the sum of the squares of the individual components. And you can actually, that's called a Euclidean norm for those of you that are really into mathematics or are going to be taking your linear algebra and your engineering analysis courses soon. But how do they actually come about with that? How could you actually prove it? Well, as engineers, we're always going to try to simplify things into kind of problems that we already know. So even if we didn't know how to compute the magnitude of a vector in 3 dimensions, we could just make it up into a series of sequential 2-dimensional problems. And that's what they're actually doing here. If you notice this blue triangle, they're basically forming a right triangle that consists of the hypotenuse of the actual vector itself. One of the bases is aligned along the z-axis, so it has length corresponding to the z component az. And this other base of the triangle is in the xy plane, and its orientation is going to vary depending on what the vector is. But if you notice, and we'll call this more formally a little bit later, this side length that we're denoting as A prime is actually called the projection of A into the xy plane. So naturally, I could talk about the relationship between the magnitude of A and this AZ term, which is the Z component, and this projection of A into the xy plane. It simply would be, it's just a 2-dimensional problem, right? It's the square root of AZ squared plus this term squared. However, I can also break this down or decompose it in terms of the x and y components, namely, this is just the square root of the sum of these two squares. And if you plug all that in, you prove to yourself that you get what you have in that formula. And I won't bore you with it because I know if you're just watching me talk, you're like, probably okay, makes sense. But you can actually take the time and sit down and prove it to yourself. So coordinate direction angles. I think this is a pretty unique thing to your book that you probably didn't see in calculus. So I will say a little bit more about this. But if you notice, what they're actually doing there is if you have a vector in 3-dimensional space, you can always take each coordinate axis individually. And just like they did on this last drawing, notice that they're kind of forming a triangle between the actual vector and, in this case, the z coordinate axis. So you can always take any of the coordinate axes and basically form a triangle where one of the, not necessarily a triangle, but you can measure the angular displacement between the vector itself and the coordinate axes. So remember, an angle is always defined as the angular displacement between two lines. So that's all they're doing here. So if you look at what alpha is, it's hard to see in a two-dimensional drawing, but it's the angular displacement if you take and you form a plane between the x-axis and that vector A. You can always measure that angle. So alpha, beta, and gamma in this case, they are just the planar angles between the vectors and the actual coordinate axes. So notice that they're naturally always going to be defined. Remember, it's like that idea I talked about in 2 dimensions where for any reference axis, there's always 2 descriptions, but one is smaller than the other. And by convention, we do usually the smaller one, or you can break the convention by saying you have to go in the clockwise axis as well. So naturally, these quantities, these coordinate direction axes, alpha, beta, and gamma, they're always going to be between 0 and 180 degrees. Because if you think you have a number that is the coordinate axes, but it's bigger, the coordinate direction angle, but it's bigger than 180 degrees, just report the other one, because the other one must be less than 180. And in addition, one thing you should know that you kind of can prove this to yourself by just drawing some pictures in front of you. If you have a coordinate direction angle that's greater than 90 degrees, what that is telling you is that the component of that vector is going to have a negative sign. And just like everything, the way that you find these is by naturally dropping perpendiculars and doing right triangles. And in this case, you're going to get a term that involves the cosine function. And it's probably something that you may have heard before. This was a more common terminology in older engineering before a lot of our mathematical tools advanced. It's this idea of the direction cosine. So we're going to call these coordinate direction angles, alpha, beta, and gamma, are just the angles between the vector and the coordinate axes. If you take the cosine of them, we will call that the direction cosine of that particular coordinate direction angle or axis. So unit vector representation, just to talk about this, we've hit on it a lot. But a unit vector, remember, is always a vector whose magnitude is 1. And really what it's doing is it's defining the direction of the vector. So if I tell you, hey, there's a unit vector somewhere in 3-dimensional space and it points here, that describes kind of the line of action of any vector with that direction. So if you scale it by an arbitrary magnitude, you can create any vector along that line of action. So this is all that this is actually showing you here, is you can always take a vector. So say you start with a vector ax, ay, and az, and you divide each component by its magnitude. Notice that naturally a way that you could look at writing that is as just the magnitude of the vector times a unit vector. So if you do a little bit of equating these to one another, going back to the last formula, what you see in terms of those direction cosines that we talked about is that the unit vector that describes the direction of any vector A can always be written, its x component or its I hat component is just the cosine of that. And just going back and showing you what alpha was one more time, it's the cosine of that coordinate direction angle. And in similar fashion, the y hat or j component is simply the cosine of beta, which was the coordinate direction angle with the y-axis, and same thing for the z-axis. So you see a little bit of a natural formula that relates the sum of the squares of the direction cosines, namely the sum of the squares of the direction cosines have to add to 1. The big point from an engineering point of view, this is all like fun math, and this isn't really just engineering, it's just getting us ready for statics, is once you pick 2 angles in that above equation, the other is determined. And that's probably not too surprising to you, because if you think about the 2 angular descriptions that we talked about, kind of these direction cosines, along with just azimuth and elevation. Azimuth and elevation, we know we only need 2 angles. So that's what this is basically saying, is this one of these is redundant. And it's because we didn't necessarily motivate these angles by needing them. We just said, okay, if you got a vector in 3-dimensional space, I can always pick one of the 3 coordinates, I can form a plane, and I can measure angle in between them. So if you do happen to be given direction cosines in a problem in the text, you could always break the vector down or decompose it into rectangular form by taking its magnitude and multiplying by each of the direction cosines. So spherical expression of direction, just to show you this, even though I know you're more familiar with it, if you start with a vector of a given magnitude, you align it along the x-axis. Theta we will refer to as kind of they call it a spherical angle here, but I would call it an azimuth rotation angle. So by definition, they're going to measure that azimuth rotation angle as being in the xy plane and describing the rotation of the vector from the x-axis, again with a counterclockwise positive direction sense, so towards y. Once you position your vector in the xy plane, so rotate it to something, then you can position it up and down according to an elevation angle. However, your book has to be confusing here and actually measure this angle rather than the elevation from the plane. They measure the complementary angle, which is kind of the descent from the z-axis. So once you got a vector in three-dimensional space, kind of drop the perpendicular, look at its projection in the xy plane. Theta is the angle measured from the x-axis to that projection, and phi is the angle measured from the z-axis to the vector itself. And notice that once you have those two angles, you can always write a vector in rectangular form by using these trigonometric formulas. And I'm sure you've seen them before, so I won't just point at my mouse and talk. I'll just assume that you are able to make some sketches and calculate and convince yourself of that. So hopefully this was helpful to you, and I will see you in the next video with an example.